Okay, so in this problem, I've got a beam, and I want to find the lightest weight wide flange beam that will safely support this load, knowing that I have allowable bending stress of 22 KSI and allowable shear stress of 12 KSI. Okay, we're going to use Appendix B out of the back of the book, and that's that table that you see right there. We'll get to that in a little bit. The first thing I need to do, though, is I basically need to find where the maximum shear and the maximum moment are in this. So I have to do a shear and moment diagram. So I'm going to start by calculating A and B, those reaction forces. And I'll do that by summing the moments about A, where I'm going to get 16 times B minus 4 times 4 minus 8 times 10 minus 12 times 6, set that equal to 0. So from that, I find that B equals 10.5, and that makes A equal to 9.5. Okay? So I can easily draw the shear diagram. Okay, I know it starts at 9.5. Then it drops down 4 to 5.5. Then it drops down 10 to negative 4.5. Then it drops down another 6 to 10.5. Okay? And this is going to be my Vmax right here. Okay, that's the maximum shear force. Okay, and we're going to need that to make sure that it does not break in shear. Do the same thing for my moment equation. I know it's going to start and stop at 0 because there's no moments there. And these are all just going to be linear plots with slopes of 9.5, 5.5, negative 4.5, and negative 10.5. Right, so it'll start like this, going up to here. And that's going to be 38, and I get that by taking 9.5 times 4. Now it's going to have a little bit narrower slope of 5.5. 5.5 times 4 is 22, which takes that up to 60. Now it starts going back down at a negative 4.5. 4.5 times 4 is, let me see, 18. So this then becomes 42. And then 4.5 times 10.5 takes us all the way back down to 0. Okay? So this is my maximum moment. Okay, and that's where I'm going to start here. Okay, with an M max, and I guess I'll go ahead and write that right here. So M max is 60, and what I have there is kip feet. I want that in pound inches, which is actually going to be 72,000 pound inches. That way I get everything in pounds and inches like I like to do. And what I need to do is I need to figure out this value called S, okay, which is just a way that is tabulated to help us figure out what beams to actually choose for things. So my S is going to be equal to the moment divided by the sigma, where my moment is 720,000, and sigma is given in the problem statement as 22 KSI, so 22,000. So the S that I need a beam that has at least an S of 32.7 inches cubed. And that's now where I go to the table. Okay, so now knowing where the maximum moment is, knowing my allowable stress, I can now design the beam so that it has to be bigger than 32.9. So I go to my table here, and I'm going to go through what I have along here is I've got the weights. So I have a 12-inch beam, and this is going to be the depth of the beam, a 10-inch beam, and a 8-inch beam. Okay, and then the times, these are the pounds for feet. Okay, so like this first one is 87 pounds per foot. So every foot of the beam weighs 87 pounds. Generally, you want the lightest beam possible because that's the less material, will cost less money sort of thing. So what I'm going to do is for each one of these, I'm going to start at the bottom and roll up until I exceed the 32.7. So I've got this guy right here, which is equivalent to W8 by 40. I got this guy here, which is W10 by 39. And I've got this guy here, which is W12 by 26, which is going to be the answer because it is the lightest pounds per feet, right? The other ones will work. They'll hold just fine, but they're going to be more expensive because they weigh more. There's more material. So the beam that I'm going to use is W12 by 26. Okay, that is the lightest beam that will hold this. Okay, now there's one last thing I have to do, and that is I have to make sure this thing is not going to fail in shear, which it usually won't when it comes to steel. Okay, but what we do is we approximate the shear as, again, V max, which we've found already, divided by the area of just the web. Okay, now I don't have the picture here, but in your appendix, you'll see this is a wide flange beam, and it gives me lots of dimensions there. Okay, and those dimensions, I'm looking for my book here, and those dimensions, it gives you the total area, but I just want the area of the web, which is essentially the area of that inside thing. So this is D all the way to the height. Okay, and then I have thickness of the web given right there, and then I have the thickness of the flange given right there. Okay, so, and these are all depth, web, flange thickness, okay, that I'm looking for. And I'm going to use that to figure out the area of the web. Okay, so my V max, remember, is 1050. Except that's, oh no, that's in pounds. That's fine. So 10,500. And then my area is just going to be the area of that guy, which is going to be the thickness of the web, which is 0.23 times that depth, which again is about 12 inches. To be precise, it's 12.22 minus 2 of those flanges, which is 0.38. Okay, so that's the area of the web. So from that, I can find that the shear stress is 3.98, which is much less than the 12 KSI allowable. So we're fine, and that's what you'll usually find, is that it won't fail in shear. That's why we design it to hold in bending moment, and then just check that it won't fail in shear. If it did, then I'd have to beef things up, maybe choose one of those other ones, and see if I could get it to work out that way. So again, this is Appendix B in the back of your book. You use that along with knowing what the moment is, the allowable stress, to figure out what the required S needs to be for this thing to hold.